But this is from Stone Valley, a picture from Stone Valley. It's a boat. You can see a sailboat, one of these sunfish 10 footers or whatever, and it has a self-bailer in it. Self-bailer is a pretty simple idea. It's just a cowl. The water is flowing from the bow of the boat to the stern. It flows over it. It flows around it. It speeds up at the back. We know from the Venturi effect that when it speeds up, the pressure drops. And so what it does is there is a hole. In that hole sits a ping pong ball that floats when this is all upside down. It'll tend to float and stop water going into the hull. But if you're going fast enough, these pins are just to keep the ball in there. When it's going fast enough, if you have a low enough pressure on this backside, then it will suck that ball out of the hole, and it will also suck any water that exists on the bottom of the floor inside the boat. And so that's basically the construction. So you might want to, for instance, design that. And it would be okay to make a model that's one-to-one scale because it's not very big. You probably can't, there's no scale in here, but it's probably an inch or two in length, an inch maybe. And really this is basically the size of a maybe smaller than a ping pong ball. So what you might do is, you could say that, well, what we want to do is we want to figure out what the pressure is that it gets delivered at the back side of this. This one's a broken one. Whoops, that's not. What is the pressure that's delivered at the back side of this? And is it enough to be able to suck this ball out of its location? And so one way to do that would be to take this prototype, and instead of flowing water against it, you could flow air against it. And if you used air, it'd be easy to do. You could use a hairdryer or something more sophisticated than that to get some velocity going. And you could measure the pressure inside the boat with a manometer to see what the pressure drop would be under these conditions. And then that would be an easy experiment to run, perhaps easier than doing it with water, for instance. And the question is, how do you scale that up to be able to calculate what the pressure would be in the real system when you're running it with water, which is what you want to know. And so dimensional analysis is basically doing that task. It's trying to figure out exactly what measure the behaviors that you'd get in a prototype system, and being able to scale them to say exactly how that system will work. So that's where we're going with this. So by way of recapping exactly where we are, it's perhaps useful to be able to say something about where we've come from. So as we walk through this class, we've gone from looking at Bernoulli's equation. We used in week 7, not last week, but week 7, Reynolds transport theorem to derive the equation of conservation of momentum. And last week we used the energy equation and frictional losses to be able to derive what we call the Navier-Stokes equations. And so to put that maybe in perspective, then I just wanted to kind of backtrack over those three. There are 3 approaches to the same problem. So maybe talk about 3 approaches. And I'll number those as the ones we just talked about. The first is Bernoulli. And we all know what that is. It's pressure 1 over unit weight plus elevation upstream plus velocity term is equal to the same components on the other side. I guess, and let me write it out in full. So Bernoulli, since we do know some other stuff, this is what we talked about last week, is equal to P2, whoops, it's a pump head, right? P2 over gamma plus Z2 plus V2 squared over 2G plus, we haven't written it this way before, we've talked about head losses, but clearly the sum of head losses between the upstream and downstream. And so from that standpoint, that, at least for Bernoulli along a streamline, was written between an upstream and a downstream location. These were streamlined velocities. These were elevations at the 2 points. These were pressures at those points. And we could think of it as a streamline, but we could also think about it as a stream tube, which also had in it this pump head and also losses within the system. I guess perhaps I'll just do this as a circle rather than anything else. And so we could think of this as drawn that way, or we could think of it as being a tube, stream tube, that goes between upstream and downstream. Same things really, because we did talk about cross-sectional areas of these things when it comes out. But that was basically our exposition of the Bernoulli equation. We also talked about, in terms of, and these are really for conservation of momentum, we also used Reynolds transport theorem. So this stuff was week 4.2 until 5.3, as I recall. This was not. This was 7. Conservation of mass was 6, right? 7.1 to 7.3. And Reynolds transport theorem really was just the idea that you could take this geometry and you could put a box around it somehow in a general way, and you could look at the exiting of fluids across all these surfaces. So Reynolds transport theorem was basically saying the same thing. It didn't have pumps or head losses in it, but it was basically saying the same as the Bernoulli equation, because we know the Bernoulli equation, if we go back to it, this is mass times acceleration. And this is force. So acceleration, of course, is a rate of change with time of velocity. And so this is a rate of change of momentum. So we're conserving it. And if you looked already at the material from 8.3, whoops, the other thing that we also put these into is Navier-Stokes equations. And the Navier-Stokes equations were, well, in class, for those, well, for you who come to class, on last Wednesday, we talked about conservation of mass, rather, in a control volume, in what would have been 8.2, but 8.3, which we didn't have because we had the exam review. We talked about mass rates of flow in, rho v, mass rates of flow out, rho v, this conservation term, and we end up with a set of equations where this is just the coordinate system that we've used, x, y, and z. And we end up with a differential equation that comes out of that. And so this differential equation actually mimics these behaviors. Actually, how do I want to do this? Yeah. And is equivalent. So if I write the Navier-Stokes equations, which you'll see if you go to 8.3, so this is 8.3. And the Navier-Stokes equations look something like velocity, rate of change of velocity with location, dv dx, is equal to rate of change of pressure with location. This is just one of them in the x direction, plus rho g plus mu rate of change of velocity with x squared. And these would be velocities, by the way, in the x direction. So without belaboring the point, Navier-Stokes equations, you can see there's a velocity in the x, y, and z. So there'll be 3 variables of velocity. There's a pressure. So there are 4 variables, so you need 4 equations to close it. So you have 3 equations that look like this in x, y, and z, and you have 1 equation in terms of continuity that allows you to solve it. That's not important to this class. But what is important to this class is the makeup of these individual relationships. And that they also have some commonality with what would be present within the Bernoulli equation. And so if I take this and a different color, I write down what this exactly is, but write it in a slightly different way. The term that includes inertia is this one. The term that includes pressure heads is this one. And the term that includes elevation is this one. And I'm going to move this to the other side. Let's not worry about the signs for now. You see that this is an equals, etc. But the point I wanted to make is that each of these expressions has a corollary that is just the same equation. It's just stated in a different way. So this, the Navier-Stokes equations, is conservation momentum in the x direction into a cube, and Bernoulli equation is conservation momentum along a streamline that may have some head losses added to it. And so these terms are directly equivalent to each other. So this is, if you like, mass times acceleration is equal to force, essentially. And this is head losses. This is frictional loss, HL. And so these are directly equivalent to each other. And so the reason for doing this, it may seem like a kind of long-winded way of doing it. The reason for doing this is that we certainly, actually the first time we met, maybe the second time we met, we talked about the fact that if you're adding apples to apples, they should be apples that you're adding to apples and not oranges, and so they had to have the same dimensions. And so we actually looked at some ratios of things that together, actually we looked at the ratios of the Bernoulli components, which together would give us some behaviors that we could define as Reynolds number, Euler number. I'm not sure exactly which ones we did. And so what we could do is we could look at what these individual terms are and see what they are in terms of units. So in terms of these Navier-Stokes equations, what are the units that are present here? We could do it, well, if we knew what the viscosity was, it's Pascal seconds, but it's kind of a complicated one. If we take one of these terms and figure out what the units are, might be useful to us to be able to move between these in a logical way. So if we take the dp dx term, so pressure divided by length, a change in pressure with length. Pressure is in units of newtons per meter squared. Length is in terms of meters. So in other words, it's newtons per meter cubed. So this equation is basically written in terms of a force per unit volume. It's just normalized by the volume of the cube, if you like, is one way to think about it. We know that these, what are the units of the Bernoulli equation? You know this. It's a rhetorical question, I guess. You know that the units of head or length are indeed length. So if we wanted to make Bernoulli equation in terms of exactly the same parameters, if you like, that exist in here, so if you wanted to make the Bernoulli equation the same units as this Navier-Stokes equations, what we could do is we could multiply it by newtons, and I guess it would be and divide by meters to the fourth. That give us right? That would be newtons per meters to the fourth. And so what units could we use that multiplying it by that would give us this? Well, we know that, for instance, this would be the same as meters. Newtons per meter cubed is unit weight, right? This is newtons per meter cubed. And so if we multiply it by unit weight and we divide it through by a length such as z, then this would now have the same units. So why don't we take Bernoulli's equation and arbitrarily just multiply it through by unit weight and z. And so now these two equations are both written in terms of a body force per unit volume. Right. It may seem completely arbitrary and stupid to do that, but there is some rationale to do it. So do we have some space here? Yeah, I do. Okay. So what I want to do now is that we label these components as different behaviors. So this first term, the first term here is inertia. So in other words, taking a ball, throwing it, changing its velocity, and accelerating it is mass times acceleration. That's what that force is. It's the same force as when the ball hits you in the chest, or when the jet engine pushes you off the runway at San Francisco International. That's inertial forces. It's inertia being converted to pressure. Second one is pressure. This is gravitational potential, and this is viscous losses. So they're roughly aligned with these. So these four things are these four in sequence. These are exactly the same as those terms in here. This is inertia, this is pressure, this is potential energy by elevation, and this is the viscous losses. And so what we could do is we could look at these individual terms. Well, why don't I write them under here? V squared over 2g, pressure, P over gamma, elevation, and HL. And this term here is going to be equal to, well, I'll write it as HL for now. And so we've done some examples. And so the examples that we've run so far and if you recall, the first ones were, if I draw my little cartoon, we talked about the fact that if you're looking at the fluid pressures that exist on the front of a submarine, or on the tip of the nose of a diving loon, or for that matter, the jet engine with the truck running behind it, wheels on it. We did some analyses, and they involved these different parameters. And in the case of this, if you remember, we used Bernoulli. And so what we could do is we could look at the ratio of these two parameters. So if we look at the ratio, what do we get? Where am I going to write it? If we take this one, and we divide it by this, it's thinking, don't think too long, v squared over 2g. And we get rid of some of the terms. I guess we've got a g here we don't need. We've got a 2 we don't care about because we're just looking at the units. Then we have pressure divided by rho v squared. Not pressure. Pressure on the top, rho v squared. If we zip up to here, you'll see that the essential physics of that problem, fluid going at some velocity, some distance away from you, v squared over 2g, going at zero velocity where it hits your chest, takes all the energy that's in the velocity, inertial term, and puts it into pressure on your chest, hence the ratio of those two components. This is the Euler number, after the Swiss physicist. And so this is an important ratio. It's basically a ratio of pressure to inertial forces, as we will see as we go through this. But we've got it just by dividing the two by the other, one by the other. We did, so that's the first example. So that goes across here. Another example we did was the equations of a free jet. And you'll recall from the geometry, for zero velocity on the top surface, that the velocity of a free jet is 2gh. Good number to remember. And again, we did it with Bernoulli. And in this particular case, that is a little bit similar to looking at the velocity term and this. So if we do the same manipulation that we just did already, and we take, for instance, the ratio of the inertial term to gravity, so if we just work out the ratio of those, so the inertial term is v squared over 2g, divided by the gravity term, which is 1 over z, we end up with v squared over 2gz. And if you take the square root of that, which we can, right, we can do whatever we want, you start seeing something quite similar to this. It's actually just then square root v over gz. We don't care about the 2. We're just interested in the scaling of the parameter. It has a 2 in it, has a 10 in it, it's a constant. And if you zip back up here, then this is exactly this number here, which is called the Froude number. Which is equal to v over gz, square root. And so this is an important number when you're looking at boats plowing through water. So you're going at some velocity, and this, if you recognize it, if this is the depth of the ocean, this is the velocity of the celerity wave, a wave traveling, a rippling wave traveling across a body of water. And so when you're pushing a boat through the water, you get this bow wave. You don't want a bow wave because you've got to kind of climb up over it. It's kind of a dynamic thing. And so the less of a bow wave you can introduce, the better off you are. And so for free surface flows, like dragging ships through water tanks to be able to figure out what their drag is, to try and minimize it, the Froude number is an important number. And it's the ratio, as we said, of inertial forces to gravity forces, right? Inertia to gravity. So another important number. We had 3 numbers on the top part. These ones are the easiest ones to do. And of course, we could have done these without making any modification of this relationship according to the Navier-Stokes equations. So now, the other relationship that's going to be important to us, and we've not really used it. I guess we have used it. And it's going to rely on the fact that we look at the ratio of viscous forces to inertia forces. Probably the most important dimensionless number in fluid mechanics, the Reynolds number. And have we done at the end? So in 8.3 also, there's a discussion on using the Navier-Stokes equations to be able to figure out exactly what the velocities in a pipe are. And if you look back at that material, you'll see that the velocity profile is some kind of parabolic shape. It's anchored to zero velocity at the walls of the pipe. and it has a maximum velocity in the middle, and it's parabolic. And that comes out of solving this set of equations here. We don't need to do it here. We did it in 8.3. But the important thing is to know that there's some distribution of velocity as you go across the pipe, which is not uniform. But for our intents and purposes, we'll make it into an equivalent uniform velocity where the area underneath each of these figures is the same. So in other words, we want an equivalent velocity on average to equal these velocities, which happens to be 0 at the edges but large in the middle. And this is an equivalent average velocity which is smaller than the maximum but certainly bigger than the minimum. And so we'll use that. And so again, we can look at the Reynolds number. And the Reynolds number, by definition, is the ratio of viscous to inertial forces, both forces. And so now here comes the reason for our manipulation. So what we said before is that this is an equation now which, instead of just defining this as a length, has a number in it that relates it to velocity. If we want to be able to compare this HL to a real number, then we need to be able to define the Bernoulli equation in terms of this real number. So if you look at the viscous forces in terms of Bernoulli, the viscous forces are going to be mu v squared over x squared. Let's call it z squared, actually. So this term here, viscosity, velocity, and some length scale squared. So this is wrong, right? It's not squared. So viscosity, velocity, and this term squared. And we're going to divide it through by the inertial forces. So the inertial forces are going to be this. But remember to put them in the same units, so we have to also multiply by this, right? So this is going to be, hopefully this will work out for us. So this is v squared over 2g. But also there's a unit weight and a z involved, so this is going to be rho g z. Okay? So this term here, I'm putting a dash around, is just 1 over this term here. Remember? We wanted to make these apples and apples. And so if I simplify that out, what do we end up getting? Looks a bit nasty right now. Well, we've got a velocity here and a velocity squared. We've got a gravity here and a gravity here. We don't care about the 2. We've got a z here and a z squared here. Okay, and so we end up with, there's a 2 still in there, which I'll keep in. There's a viscosity in there. There's a v over rho z, and that's not the right term. It should be velocity, density, length scale divided by by mu. Oh, we do have that. Okay, all right, so that's fine. We have 1, do we have 1 over? Yeah, all right. Inertial, Reynolds number is not in viscous, it's 1 over that. So this is equal to 1 over Reynolds number. So I did do it right. And this is 1 over. So it's the ratio of inertial forces to viscous forces. And this indeed is the Reynolds number. And so these 3 numbers, the Euler number, the Froude number, and the Reynolds number, are the 3 important parameters that we'll use in dimensional analysis. And so the idea is, if you want to solve your fluid mechanics problem, you don't need to solve any equations per se. You can just do clever experiments and measure some interesting things and do a minimum number of experiments and then relate them through using these non-dimensional parameters. And so this would be the same as running your model airplane in the wind tunnel, measuring the forces on it, and then figuring out exactly how you scale up those forces to represent the full-scale prototype that you'd use. Okay. So yeah, I guess that did work out. So it's a bit messier, so I apologize for that. But actually, maybe it's worthwhile not worrying so much about those derivations, but it's interesting to see where they come from, right? The basic idea is that they've all come from the terms that exist in Bernoulli. Inertia, pressure, gravity or potential energy forces, and head losses. Various combinations of those are important ratios of behaviors which are important. The most straightforward to see, I think, is this Euler number. A velocity far away from you, v squared over 2g, that's the amount of kinetic energy it has, or you change that kinetic energy as change in momentum as it hits you, and it delivers to you a pressure on your chest rather than the velocity it has far away from you. And so the ratio of those say something basically about that Euler number would be the right scaling number that we'd use if we wanted to make some charts that describe that problem. Okay. So here they are. So these are the numbers that we'll use. And I guess the Uber number, the one that has the greatest influence, Uber means above all, right, in German. I'm not sure why they use it for a taxi calling company, but yeah, who knows? Perhaps they arrived there first, who knows? But this is the ratio of inertia. So this is inertia to viscous forces. And this is by far the most important of the numbers that we'll deal with. Osborne-Reynolds' number. Because this defines exactly what the flow regime is. Once we have the right flow regime, if we measure the pressures that are applied on a structure, for instance, at a given velocity, this Euler number allows us to be able to calibrate exactly what the forces are that are applied on that structure. But to get the right forces and to have them representative of the right flow regime, the flow regime, if you like, is indexed relative to the Reynolds number. And so the Reynolds number is by far the most important of our components, because this will give us what we call dynamic similitude. And that is that the flow regime that we have acting on our structure is exactly the one that we think it should be. And maybe an exposition of that, if I go back, I don't know if it's still up here. It is, right. This one. All kinds of stuff going on. So when we were talking about this, we mentioned that when we go a bit further forward in this, and we see that the velocity speeds up, so that the tail at the back lifts up, then the flow pattern is, instead of being lumped over the wing with some curvature, it's almost dead flat as the tail comes up. So the velocity here is increasing as things are going on. There'll be greater lift applied to the wing in this particular case, and the flow patterns that result from that, it's backing off again, and you see it curving around. And so each of those flow regimes would be indexed relative to the Reynolds number. And so that's why the Reynolds number is particularly important. So a different example of that maybe is to look in these notes in the portion that we're going to show. And this is some kind of Schlieren diagram of a flow going past a cylinder. And so you take a picture of it, a snapshot in time. You know from our Bernoulli ideas of stagnation points that the flow comes around here, it splits around either side. If it was a laminar flow in a treacle or in maple syrup, then we'd expect the flow regime under very low velocities to basically look like this. It would go around here hugging the cylinder on either side. It would join again here, and the flow regime would look, the streamlines would look exactly like this, if you can see the red on there. If you increase the velocity, and this velocity is done for a Reynolds number of, I think, of 2000. So in other words, this behavior that I just drew might be for a Reynolds number of 1, say, low number. Or in other words, at least a Reynolds number which is less than 2000, or say 1000. And so this is this creeping flow where there's no separation on the backside. This particular behavior that we see here is for a Reynolds number that's, I think, 2000. So if you know what the density of your fluid is, you know its viscosity, you know a length scale, which would typically be some characteristic length scale. It would probably be the diameter in this particular case, would make sense. And if you increase the velocity from some small number to some larger number, then you increase the Reynolds number. And so what you see here is this behavior where you have a vortex that has come off here, a vortex which is here, and we're just about to get another vortex forming here. So the idea is that this flow is kind of unstable. It flows past here, ping, a vortex forms behind it, and then this drops off and gets carried downstream. Then on the other side, a vortex comes, this gets pulled downstream, and then these come in succession. They're called von Karman vortex streets because they go downstream with this progression. And I don't know that we necessarily looked at it yet in this class this year, but probably from your high school physics classes, you'll remember the Tacoma Narrows Bridge, which is a suspension bridge, was a suspension bridge with a deck suspended on it, if you recall. And all that was happening to this bridge was in the 1950s. There was a constant wind that was blown across it. People really didn't understand completely the ideas of aeroelasticity. So this bridge deck, this is the section of this deck which is suspended. There's a velocity across it. It comes across the top and down across the bottom. And so at very low flow velocities, it'll be just like this. It'll hug this and it'll just go downstream. If you increase the velocity so you get this occurring, then what it does is it sheds a vortex on the top, then it sheds a vortex on the bottom, then it sheds one on the top, then on the bottom. And so these things, it's just like plucking a guitar. It puts energy into the system, bangs the top, bangs the bottom, and it does it if it's a steady wind at such a rhythmic frequency. If the frequency that's forcing it is exactly the same as the resonant frequency of that bridge, then it starts falling apart. And you get the behavior that was ultimately in that bridge. Actually, we'd probably find it. So can we, Tacoma Narrows, right? So-called galloping Gertie. We want video. Yeah, fine. Yeah, so this is 1950s. So amazing, right? So here you have wind blowing, I have no idea which direction, but it's blowing across it because as it goes, say it's going from left to right, as it comes off on the right-hand side, it sheds an eddy off first on the top part of the deck, lower part of the deck, and it does it as exactly the same frequency, which is just like plucking a guitar as the resonant frequency. And ultimately, if you go on further in time, this is the bridge that ultimately, not the bridge you want to be walking on, driving on. Ultimately, it pulls itself to pieces. So. And so we're wiser than that, except we're not completely wiser than that, because I think 10 years ago, maybe 16 years ago, the Millennium Bridge in London was a walking bridge, which everyone got sick walking across because it had this this motion to it, which was because of wind blowing up the Thames and had this behavior. And so, in this particular case, to kind of orient us to why we're talking about these things, the interesting information for us that we've made this point is that this most important parameter that we'd like to figure out is what is the Reynolds number of the flow. Because if we know the Reynolds number, if it's a low number, then the flow across this bridge will look like this. And if it's high, it will look like this. And so clearly, if we want to measure something which is relevant for the particular flow regime which we find ourselves in, the experiments that we want to do in the laboratory or in the wind tunnel have to be at the right geometry of the flow field. Otherwise, measuring the forces that are applied on the cylinder, right? You could measure what the drag force is that you have to apply to keep this cylinder in place. If the flow regime is not the right flow regime, then we won't be measuring the right thing. So we can measure whatever we like, but it won't be the right one. So typically the approach in dimensional analysis is you do a model study, you have a flow that occurs at the right flow regime. It doesn't necessarily have to be the same fluid that you're using. You could be doing an airplane study in a liquid water tank, or you could be doing this sunfish self-bailer in an air rather than water. But so long as you get the flow regime right through the Reynolds number, then you have a chance that you're measuring the right thing. And then you'd measure what so we can also write the Euler number as being, a pressure is just a force divided by an area, 1 over rho v squared. So if you measure the force that's being applied on the cylinder as the fluid goes past it, you have this. You know what the cross-sectional area that it sees front on would be as well. You have a magnitude of the velocity at which this flow is occurring, so you could measure the Euler number. And so what we'll find out is that if we plot magnitudes of Reynolds number versus Euler number, so you can think of this as just the pressure that's applied on this thing, we'll get some relationship. And these relationships will start looking like this. And it really doesn't matter whether we're looking at, for instance, flow which is hitting against a cylinder. You know, you could also imagine this being the cylinder, being a cylinder which is edge on, where the flow, if you capped off this front, the flow would be coming here, going around it, and you can measure the force that you have to apply here, which is what would go into this Euler number, for a given velocity. Or you could think about this pipe as being an open pipe in which the flow is going through it, and in which case the velocity distribution would be something like this. And you can imagine that you're holding this pipe with a force on the outside to stop it being moved. And the reason for that is if you looked at the pressure that is applied across the length of this pipe, there's a pressure on the upstream part, there's no pressure on the downstream part. So to physically hold that pipe in place, you're having to hold it against that pressure. And that pressure is basically the drag force on the inside of this pipe. So all of the relationships that we'll look at are in terms of these two numbers, Euler number and Reynolds number. Reynolds number is the Uber dog, and Euler is the subservient one in these particular cases. But that's kind of a theme in what we'll deal with. All right?